No, no pressure move. Better.
Flip mode, flip mode. I wanna see the comments and everything. Keep it up. Shit. Keep it up, boys.
Good morning, colleagues and students. And you are welcome for today's presentation. So maybe if I can just give you an overview of what is happening, is that the person that is going to present today, colleagues, is our undergraduate student. And he is observe something and we would like to show with us or to share with us what's going on. So today actually is for us to help him polish this idea and assist when we can.
We are here.
So let us not attack him. We will need to ask some questions, but just keep in mind, he's still learning this journey, right? So our presenter is Sekwan Prince Ibaela.
Algebraic master. Algebra. Oh, algebra. Oh, algebraic master. How Mr. DUCAP?
Okay, so we'll be presenting about the DUCAPs, then you just explain to us what is DUCAPs, what is the thing with DUCAPs. So,
Guys, you can ask questions if you want.
Can you switch off the lights?
Maybe switch off the lights.
Oh, Prince Tebela.
Fine.
My boy. Good morning to everyone. As mentioned, Prince Tebela, and the title of today is DUCAPs Geometry of Constraint Sheets. Right. Now, my outline for today is that we'll talk about the introduction there, and then I'll give you a brief about my abstraction, problem statement, and aim statement, and take you through the whole idea of why I need to show you guys about DUCAPs. Right. So, the study, or rather in this talk today, our main focus is that I'm going to be introducing a new class of geometric structures, right? Named DUCAPs. So you need to understand what DUCAP stands for, which is diagonal uniform circular arc shapes. And the study obviously was meant to examine the mathematical properties under geometric constraints, right? And DUCAPs are geometrically constructed. As we know, most shapes are actually constructed. So DUCAPs are in fact constructed. And obviously it means that it is a composite of shapes, okay, that are defined by their constraints to form this family of DUCAPs. And now, in terms of the shape its own, is that the shape can be geometrically modeled into 2Ds, and it can also be modeled into 3Ds. And the existence of those shapes in those planes allowed us to actually, or allowed them to have their own unique formulas for calculating area, perimeter, and volume. So, DUCAPs, one of the other most interesting facts about DUCAPs is that when modeled in 2Ds, they degenerate into a circle. And then when modeled into 3Ds, they degenerate into a sphere. And one thing that we need to understand is what is geometry, or rather the term geometry was actually, or rather it means F measure. Okay? And geometric patterns. So can I continue for a while? So geometry just means F measure, right? And geometry actually began several thousand years ago, which was strictly meant for to be useful under agriculture, astronomy, construction of buildings, and also to solve mathematical problems. All right, and those principles includes length, angle, area, and volume. So the evidence of geometry on its own was found in all cultures, and geometric patterns obviously were useful to structure buildings and utensils, which is your working. How can I explain it? Your spanners. Do you see spanners now? Yeah, those are your utensils. And another thing is that that's tough. It was meant to structure buildings and utensils, which then reflects on the fact that geometry analyzes the creation of design and structure, and we have quite a variety of shapes, which is your rectangle, the triangle, kite, circle, and square, also including a cube and a sphere. Obviously, there's more shapes, but what I want to talk about specifically is to just give you a background of a square. So the concept of a square actually in geometry is fundamental, or it has been fundamental for centuries, and it was meant to be used in measuring areas of enclosed structures, right? And the use of the square actually started from the Mesopotamia to Egyptians, then Greeks, and Romans, which still a square in this modern times is still an important shape in geometry. Now, a square is actually important because of its own properties, which says that all sides are equal in length and that all interior angles are equal to 90 degrees, right? And another most interesting fact that I want to bring forth to you is that one of the very most, should I say, the longest existing shape is a circle. Because a circle on its own, the word circle was derived from the Greeks. Okay? And one of the most interesting things is that a circle has actually been known before history, before the beginning of recorded history, which I think is cool. Don't you think it's cool, that thing? And because of the natural circles that we would observe would be your moon and the sun. So that's why we say that it has been known before the beginning of recorded history. Right. And circular shapes were actually studied during the times of ancient Greece by the mathematicians likes of Euclid and others. And a circle on its own is also important because of its own properties, which says that every point is the same distance from the center, and that a circle has perfect symmetry. Now, we start to explain what a DUCAP is, which is the main idea that we came here for, right? Now, DUCAPs, they are constructed by dividing a shape into uniform circular sectors, and then we join those sectors by a circular arc. All right? Now, we need to then understand something about DUCAPs. There to say that it has diagonals, but its own diagonals, they are meant for structural guidance, allowing us to actually, they're allowing us to be able to actually find consistency in comparing the sectors. Yeah? Now, my motivation for bringing DUCAPs is the following, which I think on this one I'll also need a marker to take you through why I say that about my motivation. It is that for me to actually construct DUCAPs was, I took a square, right? I took a square and I fitted a circle inside perfectly. If you have a square like this, and what I did is that I fitted a circle, even though my drawing might not be perfect, I fitted a circle perfectly in here. What I've done is that I wanted to calculate the area difference of these two shapes. That's why I said that DUCAPs are in fact a composite of two shapes, right? But we know by properties of squares to say that this whole side is the same as this one, is the same as this one, is the same as this one. But because of the tangency of that circle there, it means this part will be the same as this one, and this part will be the same as this one, because it's inside a square, right? But then,
can you guys hear him?
My question didn't just underlie from the area difference. I wanted to understand that what would happen if we were to calculate this. You see this piece now? If you draw those pieces, sorry, I have to draw them again. If you draw those pieces like this, separately, right? If you draw them separately and you bring them together, it takes you back to the very same shape that you had, right? But then the idea was, let's then swap this sector with this sector, and let's swap this sector with this sector. Then they form something like this when they are separated, right? But the idea was, what if we actually closed those sectors and made them one, which form something like this? Then I wanted to understand that, or rather, by doing that, it raised a question to say, how will we be able to calculate an area of more sectors, but that will have the same geometric properties as this one? But when we have a lot of them, and we have to also close them, that's where the question raised. Now, by doing that, it enabled me to develop a general formula for their area and to explore more extensions towards volume in higher dimensions. And DUCAPs impose constraint-driven geometry by providing a foundation for exploring its potential application and optimization. And now, the purpose of DUCAPs is to examine the mathematical properties, as I mentioned, under geometric constraints. Now, my problem statement there says that most of geometry focuses more on common shapes with known formulas for area and perimeter. However, there is limited research, right, on constrained geometry, such as DUCAPs and their geometric properties. And as a result, there is no general mathematical framework for studying their area, structure, and possibly higher dimension extensions, right? So my aim is that I derive general formulas for shapes that are governed by internal geometric constraints such as angular relationships and fixed diagonals. So what's interesting is this is the visuals of DUCAPs in 2Ds. When you see there, you have DUCAP 2, you have DUCAP 2 just only has 4 vertices, whereas DUCAP 3 has 6 vertices. Then you have 4 DUCAP, which has 8 vertices, and so forth. So these are the only DUCAPs that I could possibly show you, but there exist a lot of them. But the idea is you must understand that there are geometrically there's geometry constraints of angular relationships, meaning that this angle here is the same as this one, is the same as this one, is the same as this one, is the same as this one. In each and every DUCAP, the angle between those diagonals is uniform. Alright? And if you ever have any other line that does not form a uniform angle, then that's not a DUCAP. Alright? Now, when we have to focus on, apologies for that. So when we have to focus on DUCAPs under 2D, there's a theorem by Joseph Emily Barbies, which he published this theorem called Barbies' theorem, which says that, which states that all shapes with constant width have the same perimeter. So I did manage to actually calculate the perimeter of DUCAPs, but after doing some research there, I found that I could have just used that theorem to conclude about perimeter of DUCAPs. So I did reference the fact that Joseph Emily did publish a theorem about that. So which the formula, I don't think it's showing there, my apologies for that one. So the formula says that they all have the same perimeter, which is pi d, which means that the d there is your diagonal length, right? Now, what's more interesting is jumping into the area formula under 2Ds. Each and every DUCAP under 2D, we can calculate its area by just using that formula. But obviously by tradition, it means we could be able to calculate each and every sector, the area of each and every sector singularly, and then add them together. But what I've done is, I've actually calculated area of DUCAP 2, DUCAP 3, 4 separately, and then I studied the patterns in terms of what is actually increasing in their value, and then that is where the formula comes from. And N then just represents the number of diagonals present in the DUCAP, and then D there represents the length of the diagonals from one vertices to the next, meaning that the diagonal will be from here to that vertices, and also from here to that vertices. And then theta there is the size of the angle between the diagonals, and of which we know that angles around the point is 2 pi, right? So for you to be able to calculate the theta there, you just have to divide it by the number of diagonals you have, which will tell you how many angular sectors you actually have. Yeah? And now another interesting part would then be if we have to, unfortunately I didn't bring a calculator, I wanted us to do a bit of calculations to see that it actually works, which, let me just do it like that. We know that if, all right, thank you very much. So the idea is, if you had something like this, for you to be able to calculate the area of this one, provided you have that angle right there, we can actually calculate the area of that sector by doing what? By saying it's R the area will be R equals to pi R, no, not pi R. It's the angle, which is this angle right here. Eh? The angle which is right there, and then R squared. So that angle then, because of its pi on its own, then that means if you break it down, in terms of for you to be able to calculate it, because of that angle is 90 degrees, and we know that 90 degrees in terms of radians is just how much? It's pi over 2. So if you say pi over 2, then the radius there of this particular sector, which we can call it, because of if it was constructed from a square, it would be a whole diagonal, right? But then because of it's no longer a full diagonal, we can then say it's going to be half of what? Of that diagonal, right? So we square it. By doing that, that means when we have to multiply that by the number of sectors available in each and every DUCAP there, you will end up forming that area form. And those ones below there, it's just models of 3Ds. And the question is, I need to acknowledge the fact that on this one, I did actually use an AI generator for it to help me model DUCAPs into 3Ds because of lack of software that can allow me to do that. But what I did is I provided it with just a drawing of these skeletons for it to form uniform shapes. All right, this is how they would look in 3D. Now, for us to be able to calculate the volume of DUCAPs, but I'll only just do one example in terms of how they look like in terms of drawing by using DUCAP number 2. DUCAP number 2, this will be the type of diagonals that we will have, but then now its own 3D will do something like this. Meaning that it will be joined something like this when you have to draw it. I don't know whether you'll be able to see the drawing properly. I don't know whether it is. And there's going to be another one that will start there. So it doesn't really look much on a 2D plane, but the volume will be nd cubed then into 3 minus theta over 6. And same thing, and there just represents the number of diagonals present in 2D plane, not in 3D. Because if we have to calculate it in 3D, it's going to be 1, 2, 3. But then we want the number of diagonals in its own 2D plane. So that's why I'm saying it represents the number of diagonals present in the DUCAP. And then these still represent the length of the diagonal from one vertices to the next, and then the theta there still represents the angle between the diagonals in 2Ds. Now, we must not also forget that DUCAPs degenerate into a circle when modeled into 2D, because the idea that came from this is that if you have DUCAPs, like the first DUCAP is that you have 2 diagonals, right? But if you were to add more diagonals, you're going to end up having so much of less space such that you won't distinguish that circular arc right here, because there will be many diagonals. So that's what I'm saying. As the angle actually approaches 0, then the DUCAPs in 2D, they actually collapse or degenerate into a circle. Same thing applies even in a sphere. If you look at those shapes right there, if we were to have more diagonals, that means we won't be able to distinguish that circular arc there. So then it will degenerate into a sphere. So that idea can help us in optimization of systems, of which I think the idea of DUCAPs is still under development. So the application of DUCAPs will then be used in that area to say that the area, since when they collapse into a circle, the area of DUCAPs will then be equivalent to an area of a cycle, and then same thing applies with the sphere. If they collapse into, in 3D, if they collapse into a sphere, this will imply that the volume of DUCAPs, as the angle approaches zero, it will be a volume of a sphere. And my conclusion would be that, my apologies, I need to just do this one. Sorry. Now, in my presentation, I introduced the type of diagonal constraint circular arc shapes as named as DUCAPs, right? And we know that they are actually constrained by n, which is number of diagonals, d, which is the length of the diagonals, whereas also theta there, which is the size of the angle between the diagonals. And one thing that is more important from this study of DUCAPs is that DUCAPs just actually form, sorry, they don't form. What I wanted to actually leave you guys with is that DUCAPs provide a new way of thinking about constrained geometric shapes, right? And the study shows that geometric constraints can produce predictable patterns and important mathematical properties. Although the theory is still developing, I hope you guys will actually take a look into it, and I'm looking forward for questions. And apart from that, I think the department of will be.
Thank you.
Thank you very much. This was a nice presentation. Colleagues or students, do you have any comments, questions for our presenter here? Pongani?
Firstly, thank you very much for the presentation and the courage, because not any ordinary mistake can just ask to present this wonderful presentation to us. Okay, I've noted one thing, right? Since you are talking, okay, so you were working with the area. So while you were presenting or showing me your idea of how you constructed the first sheet,
Yeah.
I didn't check with the other ones, the first sheet. So I saw like it fitted in the circle, right? Inside
A square.
a square.
Yeah.
So why not, if you want to find your area, not find the area of the whole square minus the circle?
Right.
Isn't that like maybe the intuition to it?
That was the intuition, right?
Okay.
But now we need to understand that is, I like to call it, because it's interesting, I like to call it the mother of DUCAPs. It is that one, right? Because the idea comes from just understanding the area difference, right? And remember, the area difference is for those sectors at the corners. The question was, what if then those sectors were actually presented in a different manner? Hence I said, if we had to draw them separately, right? They no longer become a circle and a square, because of the idea comes from them just being like this, right? Even though it's not perfect, the idea comes from this, but we needed to swap this sector and that one to form something like this. When they are still separated, right? That's when they are still separated. But then now I said, what if then they came together, right? When they come together, they form something like this.
Yeah, but they still, the area wouldn't change if you swap them and bring them together. It will still give you the same thing.
Same thing.
Yes.
But then now the question was, what if we have more sectors that have the same geometric constraint properties?
I have a follow-up question.
Yeah.
So, what about your other shapes? You also constructed them from like the square?
No, not from the square.
So the first one only that you constructed from the square. So the other one they come from?
The other one just come from just having properties of the same
of the first one.
Which means diagonal constraint, angular constraint.
But looking at what you gave me, they can all come from a second. For example, if you fit an octagon in the square, you'll end up having the same shape.
I wasn't aware of that, but now I think I am.
No, okay, now I just wanted to comment on it.
Thank you, Bob. Any other question, colleagues?
Thank you for the nice and interesting talk. I don't know whether it's a question or it's a comment. I wanted to know what you have been done on the DUCAPs, on the literature review, and is this your contribution on the DUCAPs?
I'll then say in terms of literature review, as I said, it's still a developing theory, but when I was doing my own small research there, I didn't find something that talks about shapes that follow this same geometric constraint. So it's my contribution as to say this is a new class of shapes. So yeah.
Doc,
Yes.
thanks for the presentation. Just mine is not a question, say, for the presentation. I just wanted to understand what interested you into, or what got you interested into DUCAP or DUCAPs in the first place. And then I'm going to need you to go through your
Question. Oh yeah.
But the first question was what got you interested into DUCAPs?
What interested me was able to understand the area difference of those smaller sectors there inside the square. But then the idea was it's possible to actually form a shape of the same sectors, like, because I tried to do same sectors, but I understood that they all can be 90 degrees angle. So the angle has to actually collapse to a certain value. So I said, that means we can actually draw something similar to the first one, but then we have to just change the angle in between. And I said, how can we calculate area of the other one without having to know exactly what's going on or where were they constructed from? So then I said, there could be a formula that we can use to calculate a shape that has same thing, a similar construction. And I said, let me then.
So does that mean since the angles are equal, the areas are going to be the same?
The areas of each and every sector are going to be the same.
Now, my last question was this. The purpose or your motivation says the purpose of DUCAP is to examine the mathematical properties under geometric constraints.
Yes.
What does that mean?
It means we wanted to understand the pattern of sectors as they increase under geometric constraints. As in, like, from the first one, we had that the angle was 90 degrees, right? Then when we move to DUCAP number 3, the angle there actually reduces. But now we wanted to understand that what will happen in terms of pattern is how is the area increasing? Is it a way in which that we can actually just formulate a general formula which will allow us to just calculate those areas without having to calculate similarly each and every sector and then in there. Just enter parameters into the formula, then you get the same value.
So it's still right if we say the purpose of DUCAPs is to examine their mathematical properties under geometric constraints. That's their purpose, is to examine their properties. I just wanted to understand that.
Because when we speak about properties, as someone who's in maths, I'm thinking about a lot of things. When we say properties, I expect you to show me that a DUCAP is symmetric. Does it satisfy the convexity? Is the equivalence of a shape? Does it satisfy? Did you prove that? Yes, it's true. As n tends to infinity, you get a second. Does DUCAP really, is there a mathematical proof that DUCAP really converges to a second? So I'm expecting such properties that if you rotate DUCAP, let's say 90 degrees, you still have a DUCAP. You get my point. So I think Doug is asking based on that. Besides formulas of area, perimeter, and so on, are there other properties that we have done? Can you make can you reflect DUCAP on, let's say, y axis, and then you still get the DUCAP?
I believe you can.
Can you partition DUCAP into two and you still get DUCAP? Do you have mathematical proof that you have done?
As of yet, no, sir. The only proof that I have is the formulation of the area, formulation of the volume there.
Okay. Also, have you looked at super ellipses or spine caps to look if can you get a DUCAP from such shapes?
I haven't, because I think my main focus, even when I was still doing my smaller research, was just focused on the geometry of the shape alone, to say, does it exist? And if it exists, like one thing that I've seen on the internet as well when I was doing my research is that DUCAP 1 exists, like as in it has been there, but obviously the only focus wasn't what happens if we had similar sectors. They just said this is a shape that was formed from a square and a circle, but they never really asked what happens if we had more sectors. So I brought the idea of, if we have more sectors, angular, we have angular relationship, angular constraints, then we have a family of shapes that we can actually just generalize the formula.
Is it a polygon?
Well, by definition, I think I'll assume that it's that. Hence, I said it's a shape, because I think a polygon, in my understanding, I might be wrong, is that a polygon has to have straight lines, if I'm not mistaken.
Yeah, straight edges.
Yeah, straight edges. So I think that one is not a polygon; it's a shape. So yeah.
Someone asked if can you calculate the total surface area of the DUCAP?
Can we calculate the total surface area of a DUCAP?
Yeah.
Well, it's possible, but it leaves a gap for me to actually further the study into knowing on how to calculate the surface area of a DUCAP, especially in 3Ds, because I only ended by just calculating the volume as of yet.
No questions online.
It's only one.
Any other questions, colleagues, or comment? Remember, he needs our input so that we can assist him in brushing this.
He asked again the same person. What are its topological properties?
Well, I'm still an undergrad.
Like
Topology is another
justice.
thing.
He's actually following up on what I've just said.
Yeah. So, but just to share a little bit, I'm not saying I know about topology, but there's one topic that I just I just looked at a little bit, which is this. I think they call it isometry, if I'm not mistaken. So I think it talks about if you can actually turn into another one. So I think they are isometric because of the fact that they degenerate into a second. So I'm not saying there should be a follow-up question about them, but I'm just saying that. So yeah.
Maybe the last one from my side. So what parts on the DUCAP should remain fixed and which one can be varied? Which constraints? Because I saw already n can change depending on number of diagonal lines that you have, right? And obviously n will determine the dimension, not the dimension, but the DUCAP that you are working on. If it's n equals to 2, we have DUCAP 2, right? And so on.
And
So
so on.
n changes.
N changes, yes.
Then what about the arc
The arc length.
radius or length? Yeah.
Yeah, the circular arc there must remain fixed because of in circular geometry they also mentioned something to say that the arc length is actually dependent on the diagonal length there. So if that changes, that means the circular arc must, okay, let me rephrase. The circular arc must also still be, okay,
Varied or fixed.
it must be fixed because of the angle is the same of each and every sector. So the same length of that one will be the same as other sectors as well.
Colleagues? You have a question?
Yeah. Okay, so can I ask you something? Have you studied the
Did I?
integration? So you studied the application of integration?
Not yet.
It's okay. I just wanted to ask if it's possible for you to calculate the area of the DUCAPs using the integrals.
Oh, I think that's something I'll take note of to further the study of DUCAPs into that field as well.
Yeah.
So, yeah, just to follow up on what Sir said there. Actually, the whole thing, what I'm saying is that you're calculating, like you're doing these things manually. Calculus will make it easy for you. You'll be able to explain it more natural calculus. Like you said, for the area, you will just use one integral and say, go the area. So, please look into calculus. It will make your life with explaining. Because now you're doing, with the volumes, with the areas, and the parameters, you're doing it manually, which in how I see it, it's a bit difficult. With calculus, calculations of the area, you just do one, right? And then you'll do the area. So look into calculus.
I'll do that.
It's a comment. Don't ask you about arc length, whether it will remain the same. According to my observation, it will vary depending on the number of points and also the distance of the diameter. That's what we control like your arc. But it will be the same throughout
The
whole
shape.
circuit.
Yes.
But the thing differentiate between very because of those two sectors.
Also, maybe I would say I have a proposal. Maybe you'll think about it. Maybe we can organize another talk where it will be based on the application side. Maybe create a scenario where we can use a DUCAP. We put values there. We see if does it really work. Like he said about, no, just take that, then remove the circle, and then you have everything. Get my point? So if you do it, you compare it with that one and see what is going on. let it be something that we will be able to see so that we can have a better feeling of yes, this is going on.
I think we can actually organize that.
Mister, another question. Can this shape repeat infinitely without gaps, or it meant to stand alone as a singular focal point? That's very smart. The name Sharp. Can this shape repeat infinitely without gaps, or is it meant to stand alone as a singular focal point?
I think if someone can just he's using too much English there. I don't know if whether there's someone who can maybe simplify the question for me, but that is too much English. It's tough for me, but yeah.
Yeah, but maybe something that you should think of when you look at it. So, colleagues, thank you very much for coming, and let us give him a round of applause.
Algebra. Wow, what's any come on? The academic plug. Academic plug on myself. Lele fair no go.
Bye bye.
No, say cancel a bit. Say cancel. I don't want to go along with it. Does it prove the topological what was? Hey. Just say hi to that. Say hi to that person in faith. So what? No, I'm live. The academic plug. The academic plug.
Don't be hard on my brother.
Hey, in faith.
We understand you're from the oral school.
He's from UJ in faith.
Yo.
As we are from the purple one. We are from the purple one in faith. No sei dire mogai. I was lost. Esa. Che loro non rzeni la ta kafa yeah. Pesher che tempe. Guys, thank you for the thing. I just say hi to the algebraic team in fact. Hola. Say hi to the algebraic what?
Hello to the algebraic what?
Yeah, the online squad in fact.
Yeah, especially the academic plug.
Yeah. Hey, the academic plug in fact. Yeah, come on. Oh, Cassandra, you joined late in fact. No, I get you, my guy. I got the question again. I got the question. I will pay. Yeah. He's from UJ. This guy. The academic plug.
Academic plug.
Yeah.
He said he's gonna join.
I think it's academic plug. Come to online. Okay. Online
the presentation is already done.
So actually, what it means is that can you take that shape, squash it to a point?
Oh yeah,
you get my point. Because another infinite part that is talking about is those lines. You can make them. You can make those lines, and then we have a second. But can you also squash it to a second where you have similarities?
But we can.
But it needs a proof. You know, you can assume 1 over x as it has similarities. But in maths, you can also show that you can do something to show that there's a small similarity, non-similarity point.
I learned something. New mathematics is coming. New mathematics is coming. But yeah, guys, thank you guys for joining. It was wonderful. But now, let's do DUCAPs. They must allow us to move out. You can't get out. How
to qualify, choose.
Thank you very much, numeric. Thank you very much. Hey, they must allow us to get out.
There's someone who's sending 1,000.
Who sent 1,000?
Someone in faith.
1,000? Ow. But guys, honestly, thank you very much. I tried my best.
Stage fright is the problem.
Relax. Say, I am dancing.
How was it?
Yeah, stage fright.
Stage fright.
You were nervous, I can tell.
Yeah, I was very nervous.
Yeah,
I was very nervous.
We must take him to Great Hall in front of the
Thank you very much. Thank you very much.
We are proud of you, sir.
Yeah, it's new
Yo,
geometry.
there's this other, I think, I don't know, but then it's an old lady. She commented and said she's great.
Yeah.
Mama.
Shout out to your mom, boy.
Yes, well done.
My mom was here as well. Man. Sure.
Is your mom watching? Yeah, it's her.
Wait.
Yeah.
Yeah.
Let me see.
Hello, mom.
Oh, hello, mama.
Let's say hi to them.
Oh, fine.
She's proud, boys.
Yeah?
Oh, who wrote them down? Wow, very important someone.
This is big boy.
I think one day
Very important someone, this one.
one day you'll buy a car.
That's my book. Secretary.
That who was helping you with research, Albert.
Yeah.
Then it's like he didn't ask you because he was gonna cook you. He can't help you and cook you at the same time.
Keep the book in
And if who didn't come from our group chat, Nyan keep.
That's why guys, they're saying,
Who came then?
where's my school bag?
Say thank you, Faith.
They're saying,
Thank you so much.
thank you so much. They're saying that they are going to try and host another one where I have to talk about the applications of DUCAPs and more like we're going to deal with numerics. No university in SA is ready for you.
Obvious in faith.
I do believe they are not.
Obvious in faith.
It's gonna really take a long.
And don't forget to watch VSOP.
But guys, I literally want to cry right now, but I have to hold myself.
Yeah.
So it's a big one, guys.
Yeah, it's a big one.
Until then, guys, thank you for joining. I'll go live maybe during later on. Let's just talk about the presentation. I'll take more questions later on because now I'm leaving.
Yeah.
Thank you.
How do I cancel it?
Thank you, guys. Thank
The
you.
students are actually proud of you.
Yeah.
Cancel a
You need to go to the share.